Okay, so to show that something is linear, right? Just to remind you, it means we have to show that it respects addition and respects scalar multiplication. Those are the two steps. Okay, so let's just practice that. So t respects addition. Okay. And again, as we do this, I mean, a lot of people struggled with this at first, so this is just reminding you, and if showing this kind of thing is hard for you, be sure you go back before Monday and try some other examples. Right? Just seeing me do one example right now is not going to cut it. If it's something you're struggling with, then you're going to want to go back to it. But I just want to do one to get it back in your head again as to what this is about. So how do we do this? Yeah, I have to have two matrices, right? Okay. So let me just start off. Let's let A, B, C, D, comma, I'll use E, F, G, H maybe. These are elements of M2 of R. So we take two 2x2 matrices. You don't have to use those notations, but they work just fine. Okay, and then we have to look at T of the first one plus the second one. So remember, T respecting addition, really, this is the formula that you're trying to verify. Okay? T of the sum is the sum of the transform vectors. Okay, so I'm going to put in my first vector, which is A, B, C, D. I'm going to add it to my second vector, which is E, F, G, H, and I want to transform that thing. So what do I do first? Combine the matrices together, right? Because the formula for T, which maybe I should emphasize that here, the formula for T only tells me how to transform one single matrix at a time. So I have to make this into one single matrix. So you do that by adding them together. So T of A plus E, B plus F, C plus G, and D plus H. All right. And now we can apply the formula that we were given for the transformation. So the first entry is A minus B minus 3C. In other words, it's upper left minus upper right minus 3 times lower left. So if I apply that here, I have upper left minus upper right minus 3 times lower left. Okay, I have that. And then the second slot is 2 times the upper right, which is B plus F, plus the lower right, which is B plus H. Okay, so that's quite a bit of letters there to push around, but let's see if we can get it organized. Can you guys remind me, what do I want to do with that? This is where sometimes you start getting stuck a little bit. It's okay if that happens. You can always stop. You can always stop with that and say, I don't know what to do next. I don't know how to manipulate it. And you could say, I don't know what to do next, so I'm going to work on the other side. Because they've got to be the same, right? You're trying to show that they are the same. There is nothing wrong with starting over. Maybe I'll just do it this way. With starting over with T of each individual matrix. What you can see from this is that you're trying to get all the A, B, C, D's together, and then all of the E, F, G, H's together. So if you were looking at this and trying to figure out how can I work with that, the idea would be, let's get all the A, B, C, D's together, and then get all of the E, F, G, H's together. But that's okay. Let's just do the bottom approach here. Let's just transform them separately. Okay? So the first matrix, okay? So the first matrix, if I transform it, here's the equation, right? So I just put that in there, A minus B minus 3C, comma, 2B plus D, plus the second matrix, when I transform that one, I'm going to get what?
E minus F minus 3G.
E minus F minus 3G, comma,
2F plus H.
F plus H. Very good. Okay? We have that one, and now you have to literally add slot by slot. You starting to see it come together? Yeah? So the left slot is going to be, I'm just going to start adding this together. So A minus B minus 3C plus E minus F minus 3G. Just add all of that together. And then the second slot is 2B plus D plus 2F plus H. It's a little bit small, but that's the idea. And now you just can look at it and say, yep, that's the same as that. These are the same. So therefore they agree. So that's what you have to say. Clear enough? Okay, great. So that's showing that T respects addition. What's the second part we have to do?
Scalar multiplication.
I have to check that T respects scalar multiplication. Exactly. Okay, just two parts, just like subspaces. So how do you want me to start this one off?
Let A, B, C, D be as above, and K be as scalar.
Okay, let A, B, C, D be as above, and K is my real number. Okay? We choose a scalar, and now what we're going to do, so I'll just remind you here, for T to respect scalar multiplication, we just have to check this equation. Basically, you want to show that you can factor out the constant. K is the constant here. Okay, so we have T of K times the matrix ABCD. What should I do with that? Yeah, just distribute the K, right? So I'm not ready to transform anything yet because I don't have a single matrix there. But if I distribute the K, I'll just get KA, KB, KC, KD. And now we know how to transform that using the formula in the box. So it's just going to be upper left corner minus upper right corner minus 3 times lower left corner, comma, 2 times the upper right corner plus the lower right corner. So you just have that. And what is the natural thing to do at this point? Yeah, there's a K in every single term that you see. So let's just pull it completely out of everything. So that's kind of what you wanted to do anyway. So you just get that, and then that is equal to K of T of A, B, C, D. So far so good? Does that make sense? Okay, I've been using a blue marker for showing things that are not good. I'm going to show you something here that would be not a good thing to write down, because I see people do it, which is to put a T there. This would be really, really bad. This would get a lot of frowning faces, because now what you're saying is that you want to transform a vector in R2. But your T does not transform vectors in R2. T only accepts matrices. What you're going to notice when you look at all of this work is that anytime there's a capital T, it is always applied to a 2x2 matrix. It's never applied to a vector in R2. So it may seem like an obvious thing, but I see a lot of people make this mistake. When you're looking at these steps, some of them have a T in front of them, and some of them don't have a T at all. When I have my vector in R2, I've already transformed the vectors, and so I shouldn't have that capital T in there anymore at that point. It should be gone. Right? So yeah. So this is a clean way to write it up. Is everybody okay with that? Okay. So then the next part, there's a part B here. Go ahead and erase this. Part B is going to be to find a basis for the kernel and the range of the transformation. So we need to remember what that's all about. Kernel and range. Okay, so this is part B. Find bases for the kernel of T and for the range of T. think probably the very first thing we should do is remember what these things are. So just a quick crash course. The kernel of T. The kernel of T is a remember it's a subspace of the first vector space, right? In this case the M2 of R. So it's the set of vectors V. So if T goes, let's just write a general notation here. All right, if this is your transformation, then the kernel is those vectors in V that get killed by the transformation, right? So T of V becomes 0. So in this problem, it would be which matrices are actually showing up as outputs, right? So in this case, it would be the set of A, B, C, D, such that, well, A minus B minus 3C, comma, 2B plus D is the 0 vector of R2, which is 0, 0. So this is always a subspace, just to remind you, this is always a subspace of V. Okay, you should be able to show that. You could actually practice that. It has to be closed under addition and closed under scalar multiplication. And the reason that this is a subspace of V really boils down to the fact that T respects addition and scalar multiplication. So those properties are what make this work. So you can basically see that your kernel is just the set of A, B, C, D such that, and then you just have two equations here. A minus B minus 3C is 0, and 2B plus D is 0. So you actually have a system of equations to solve. So we can actually try and show how to solve that system then. See how this is going to use the chapter 2 stuff, solving linear systems of equations. So essentially you have a matrix that represents that system. So A minus B minus 3C, and don't forget to leave a column for D as well, is 0. And then on the second line we have 0, 2, 0, 1 augmented with 0, and you pretty much already have your row echelon form here. The pivots are looking pretty good. So which variables are the free variables?
C and D.
Yeah, C and D, right? Remember your columns correspond to your unknowns, A, B, C, and D, and C and D are the unpivoted columns. So C and D are free. So if we started writing down what C and D are, I like to use R and T as my free variables usually, right? Then I can go backwards and figure out what A and B are. So what will B equal?
-1/2.
Yeah, if you look at the bottom, well, of course you can just solve it from here. If you put in T for D and solve for B, you're going to get -1/2 of T. Right, so -1/2 T would be what B is. And then A, from the top line, A is supposed to equal B plus 3C. So B plus 3C, we can just write that down, -1/2 T plus 3R. Okay? Okay, so I've pretty much figured out how A, B, C, and D look in terms of my free variables. So what do I need to do next? Okay, I can bust out these variables. So bust out the variables. It's one of the catchphrases for Math 250B, right? Bust out the variables.
Should A be +1/2?
Oh, I'm sorry.
Oh, sorry.
No. It's equal to B plus. It equals B plus 3C if B was -1/2. Yeah. So I think we got it right. So bust out the variables. So if I do that, what I'm going to get is T times -1/2, -1/2, 0, 1, plus R times 3, 0, 1, 0. So There's busting out the variables, right? Okay, and now what do I need to do? We're working on the kernel. We were asked to find a basis for the kernel. So how do we get our basis? Are we ready to write down the answer? Yeah. We actually can. Okay, so I'm going to get out my blue marker. It means I'm writing something down that's wrong. And you guys are going to tell me what's wrong with this, I hope. So here's a bad answer. So I write that down, and I write that down. What's wrong with that? Exactly. The vectors that are in the kernel have to be 2 by 2 matrices. So be careful that you don't portray them in the wrong way. They should be represented as A, B, C, D as a 2 by 2 matrix. It's even more important when you have, if you had something like polynomials or something, right? You got to make sure that your vectors look the way that the form should look for your vector space you have. So the A, B, C, and D is perfectly fine, but they just need to be arranged correctly. So -1/2, -1/2, 0, and 1, and then comma, and then the R variable had 3, 0, 1, and 0. Like that. Okay, so there's your, oh, and this is not very good either. I should have, this should still be with my blue pen. Because if I write the kernel of T, no, you don't have to erase anything, but there's something wrong here. Can you tell me what, this would be a good check. Can you tell me something that is wrong with what I wrote right here? Is the kernel of T equal to this? It's not equal to this. There's no null space here. It's not. If you're telling me the kernel of T is equal to this, you're telling me these two vectors are the only things in the null space. Is that true? No. What else is in the null space? Exactly. All linear combinations of these, right? So I can fix this very easily, and I better fix it because this is an important difference. It's the span of that set. The kernel is equal to the span of that set. Now, if I say what is a basis for the kernel, that's a different thing. So the kernel itself is the whole span. But a basis for the kernel, then I don't want to write the word span, or otherwise I'm going to be in trouble again. Then I just want to write the set. Do you see the difference? Some people are very sort of careless with writing this word span in front of stuff. And you want to be very, very sure when are you supposed to write the word span. Span needs to be there when you're expressing your whole space in terms of that spanning set. But if you're just asked what is the spanning set or what is the basis, well then it's just that list alone with no, don't put the word span in front of it. Okay, you see the difference? We don't want to probe me any further on that. It's just the difference between what is the kernel versus what is a basis for the kernel. Those two questions are not the same, exactly the same question. Right? Okay, so that's the kernel. That's the kernel part. If you go back to the second midterm review packet and the review session that we did for that exam, you're going to find more examples of practicing this. This one, I think, relatively speaking, is a fairly easy example because your kernel is expressed just as a couple of equations, basically. It tells you what it is. But we've had other examples that I think you can go back and review. I don't think I'm going to do it now unless you guys absolutely want it. But we've done other examples where we might have taken like polynomials or something. And then we had something like this. If we took a p of x, the transformation was, you know, something like take two derivatives of it or something, right? And see, this sort of transformation, this also respects addition and scalar multiplication, as you know. But this one is a little more abstractly presented. I don't see the specific coefficients of the polynomial. And so for something like that, for something like this, you're going to have to actually take the effort to write out the vectors and then take two derivatives of it. So it'll be something like that. T of that equals that, right? And then you do it just like before. You set this part equal to 0. It creates equations involving the A, B, C, and D, and so on. I hope my voice is going to make it today. A lot of talking. Okay, that's the kernel. Any questions on that part? All right, let's talk about the range. Does anybody remember what the range is?
Everything that survives.
Not quite. What's that?
It's everything that survives the transformation.
Well, it's actually survives is kind of not quite the right word, but what it is it's the set of all of the outputs that actually show up. So in other words, if you transform all of the vectors, if you take every possible vector in the vector space and you just transform it and you see what do you get out of that transformation, that's the range. And this thing, turns out, is a subspace of W. So this is on the W side. Now, I sometimes like to draw this picture, V and W like that. If you just imagine, of course, the zero vector I always put at the bottom. Zero vector always goes to 0, and then all these other vectors are just mapping from one side to the other here. Right? This part right here, this part that I'm shading in, that is the range of T. It's inside of W, and it is a subspace of W. It's those outputs that actually show up. Okay? So for example, if my transformation starts with polynomials of degree 3 or less, like this, and it takes two derivatives of that, you can pretty much be guaranteed by the time you take two derivatives of a polynomial that has degree 3 or less, your polynomials are going to drop down in degree, right? As you take derivatives, the power rule brings them down. So your range of this kind of transformation, I didn't even specify what W is here, but your outputs are only going to be polynomials of degree 1 or less. After you differentiate a cubic polynomial twice, right? If I take this, well, we can see it right here. Right? After I started with something of degree 3, my output is only degree 1 or less. So the range of this transformation would basically be P1 of R. Even though I could have said, oh, I'm going to let W be P sub 17. It wouldn't be wrong to do that. It just means that your range of T is very small compared to the receding space W. W is the receding space for your transformation. Doesn't mean everything in W gets hit by the transformation. So, now, let me stop for a second and ask, does anybody think that they know the answer to this question of what the range of T is yet? Or what a basis for it would be? remember this moment, because in a few minutes I'm going to come back to this moment and say we could have answered those questions right now. We actually know enough to already be able to say what the range is and what a basis for the range is. But I don't want to jump into that yet because I want to stick with the more traditional approach here. So the more traditional approach, the thing that we usually do when we're trying to find the range of t, if you remember, it's simply the span of, this is how you're going to do it. If I actually ask you to do a calculation of the range of t, this is how you're going to do it. You're going to take the transformation of v1, v2, all the way up to vn, and take the span of that, and this is where v1, v2, up to vn is a basis for v. So you start with any basis for v, and you form the span of it. Okay? Form the span of it. So, you can choose whatever basis you want. So we know in this example we have 2x2 matrices. You guys probably know a very nice basis for that. You should always choose a nice basis. So essentially in this problem, so in our example, what I would recommend that you do is the range of t is the span of t of, I would use 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. It has to be a basis for whatever the v is. Usually v is like some nice vector space, like M2 of R. But it doesn't have to be. I could have done something very weird here. I could have said, my vector space is going to be the 2x2 symmetric matrices. I could have done that. Then you would have had to come up with a basis for the symmetric matrices, transform that basis, and then you'd be able to calculate the range of t.